A lot of people struggle with the concept of implicit differentiation, so I'm going to go through it slowly. So let's say we have y is equal to x to the power of 2, and if we differentiate this, we have dy over dx is equal to 2x, and hopefully that's very clear. Now, when we say that we differentiate this, what we've actually done is we've differentiated both sides. So when we differentiate x to the power of 2 this side, we get 2x. And when we differentiate this side, y, when you differentiate y, you get dy over dx. And this is the basis of implicit differentiation. Another way to say this, and a thing that will come up a lot in this video, is something like this, where d over dx, what this here means is that we're differentiating in terms of x, whatever is inside this bracket here. So this here is saying differentiate in terms of x. This y here, if you differentiate y in terms of x, you get dy over dx. You can think of this kind of y coming up here. But the main takeaway from this is that when you differentiate y, you get dy over dx. So hopefully that all makes sense, but where implicit differentiation gets more difficult is when we have to differentiate more complicated terms, such as y squared here. And the way that we differentiate terms like this is we have to use the chain rule and the product rule. So go back to the videos on the chain rule and the product rule that I've already made in this chapter if you need a reminder, because the chain rule and the product rule come up a lot when we're doing implicit differentiation. And the reason this is when we're differentiating something like y squared, we're going to treat y as if it's a function, and therefore when we're differentiating y squared, we're going to use the chain rule to differentiate this, because this is going to be a function inside another function. So if we look at y squared here, we're going to say that y is the inner function. Again, go back to the video on the chain rule if you need a reminder on the inner function, the outer function. We're going to say that y is the inner function, and we're going to say that this power of 2 here is the outer function, and the chain rule is the inner function differentiated multiplied by the outer function differentiated. So therefore, when we differentiate y squared, we're going to use the chain rule, and it's going to be the inner function differentiated, and the inner function is this y here, so it's going to be y differentiated. And we've already talked about that when you differentiate y, it's dy over dx, and then this is going to be multiplied by the outer function differentiated, which is going to be this power of 2 here differentiated. And remember, when you're differentiating a power of 2, you can think about it like x to the power of 2 here. So this 2 is going to come down as the coefficient like this here. Remember, with the chain rule, when we're differentiating the outer function, we keep the inner function constant. We kind of just ignore it. So we're still going to write this as y like this here. And now it's going to be to the power of, when you differentiate the power of 2, it's now going to be to the power of 2 minus 1, so it's going to be to the power of 1 like this, but we don't need to write this. So dy over dx multiplied by 2y, if we move this 2 to the front, it's going to be 2y dy over dx. So when we implicitly differentiate y squared, it's 2y dy over dx. So here's another example where we have to differentiate in terms of x, y, and here we have to use the product rule because we have two functions that are multiplied together. The first function is this x here, and the second function is this y here. Now go back to the video on the product rule if you need a reminder, but the product rule is that if we call one of the functions u and the other function v, then dy over dx is going to be equal to this here. So we can use the product rule on this by saying that the first function, which is x, is equal to u, and then du over dx is equal to x differentiated, which is going to be 1. And then if we call v the other function, which is this y here, and then dv over dx, remember we're differentiating in terms of x. If you differentiate y in terms of x, it's going to be dy over dx. So therefore, when we differentiate in terms of x, this xy is going to be, so we're going to use this formula here, it's going to be u, which is x, multiplied by dv over dx, which is dy over dx, plus v, which is equal to y, multiplied by du over dx, which is equal to 1, so times by 1, but we don't actually need to write that. So if we differentiate xy in terms of x, it's going to be x dy over dx plus y. So here's another example where we have to differentiate sin y in terms of x. So this is another example where we have to use the chain rule. Remember, we treat the y as a function, so the inner function is this y and the outer function is this sin here. So remember the chain rule, it's the inner function differentiated multiplied by the outer function differentiated. So if we differentiate sin y in terms of x, it's going to be the inner function differentiated, which is this y differentiated, which is dy over dx if we differentiate y, and this is multiplied by the outer function differentiated, which is going to be this sin differentiated. Remember, when you differentiate sin, you get cos, and remember the inner function remains constant when we differentiate the outer function. This is going to be cos y. So when we differentiate sin y, it's dy over dx cos y. So here's some more examples that are slightly more complicated. So for this one, we have to differentiate 4x squared y squared. So we need to use the product rule because we have two functions multiplied together, this x squared and this y squared here. So if we say that u is this here, this 4x squared, and we put the 4 with it as well, then du over dx is equal to, so this 4 coefficient just comes down like this, and this is going to be multiplied by x squared differentiated, which is going to be 2x, and then 4 times 2 is 8, so du over dx is going to be 8x. And then if we say v is equal to the other function, which is this y squared, then dv over dx is going to be, so we're going to have to use the chain rule here. We've already done y squared, but we need to use the chain rule because the inner function is the y and the outer function is the power of 2. So the inner function differentiated is the y differentiated, which is going to be the dy over dx, and this is multiplied by the outer function differentiated, so this power of 2 differentiated, so it's going to be 2y to the power of 1, but we don't write the 1, so dv over dx is 2y and then dy over dx. So remember the product rule is, if we differentiate this, it's going to be u multiplied by dv over dx, so it's going to be 4x squared multiplied by 2y dy over dx, and this is going to be plus v multiplied by du over dx, which is going to be y squared multiplied by 8x, and if we simplify this, 4 times 2 is 8, so it's going to be 8 squared y dy over dx plus 8xy squared. So here's another example where we need to differentiate x squared times the natural log of y. So we're going to have to use the product rule again because we have two functions multiplied together. So if we say that u is equal to the x squared part, then du over dx is equal to 2x. And then if we say that v is equal to the natural log of y function, therefore dv over dx is going to be, so we need to use the chain rule here with the inner function being this y and the outer function being this natural log. So the inner function differentiated is going to be y differentiated, which is going to be the dy over dx, and this is going to be multiplied by the outer function differentiated, so this natural log differentiated. We've talked about in this chapter, in the first video in this chapter, that when you differentiate a natural log, it becomes 1 over and then whatever is inside the natural log, so it's going to become 1 over y, so dv over dx is equal to 1 over y multiplied by dy over dx. So that means when you differentiate this here, it's going to be u multiplied by dv over dx, which is going to be x squared over y dy over dx, and then this is going to be plus v multiplied by du over dx, which is going to be 2x times the natural log of y. And then let's just do one more example where we need to differentiate y cubed cos of x. So we need to use the product rule because we've got two functions multiplied together. So if we say u is the y to the power of 3, then du over dx is going to be equal to, so we need to use the chain rule with the inner function being the y and the outer function being the power of 3. So the inner function differentiated is going to be the y differentiated, which is going to be the dy over dx as always, and this is going to be multiplied by the outer function differentiated, which is going to be this power of 3 differentiated, which is going to be, so this 3 is going to come down as the coefficient, and then it's going to be y, and now it's going to be to the power of 2. So du over dx is equal to 3y squared dy over dx, and then if we call v the cos of x, and dv over dx is equal to minus sin of x. So dy over dx is equal to u multiplied by dv over dx, which is going to be minus y cubed sin of x, and this is going to be plus v multiplied by du over dx, which is going to be 3y squared dy over dx cos of x. Now, really quick, the reason that we're implicitly differentiating y is because we're differentiating in terms of x. So when we differentiate y, because we're doing it in terms of x, we implicitly differentiate to get dy over dx. If we do the exact same differentiation, but we now do it in terms of y, it's the exact same logic, but now the process switches around. So if we were going to differentiate this xy in terms of y, what would happen is we'd still do the same product rule because it's two functions multiplied together, so u would be equal to x. But now we're differentiating in terms of y. Now we differentiate the x implicitly and it becomes dx over dy when you differentiate x in terms of y. And now if we call the v the y and we differentiate this in terms of y, now the y basically becomes the x and it differentiates the way that the x does up here. So if v is equal to y, dv over dy is equal to 1. It'd be the exact same thing as if we were differentiating in terms of y, xy to the power of 2. So now v would be equal to y to the power of 2, and then dv over dy, because we're differentiating in terms of y, it would act as the x. So y squared differentiated would be 2y. So why does any of this actually matter? When do we use this? Well, all throughout differentiation so far, we've been differentiating y is equal to a function of x, like y is equal to x squared or y is equal to sin of x plus x to the power of 3. Equations like this, where y is the subject. But sometimes it won't be like this. Sometimes it will be like this here, where both y and x are involved in the equation that you need to differentiate, and there will be no way to rearrange to make y the subject. So let's do this example here where we have x squared plus y squared is equal to xy plus 6, and we need to find dy over dx in terms of y and x. And the way that we do this is we differentiate both sides of this equation and then we rearrange in order to make dy over dx the subject. So let's do this. So if we differentiate both sides, so let's start with this side here. If you differentiate x squared, it becomes 2x, and if you differentiate y squared, it becomes, I've already gone through this quite a few times in this video, so I'm not going to go through it completely, but use the chain rule and then you get 2y dy over dx. So that's the terms on this side differentiated, and if we differentiate the terms on this side, if you differentiate xy, it's going to be, again, I've already gone through this in this video, we use the product rule. We say that u is equal to x, du over dx is equal to 1, and then v is equal to y, so dv over dx is equal to dy over dx. So then we get this x dy over dx plus y when we differentiate xy. And then if you differentiate 6, remember when you differentiate any constant it's just 0, so this just goes away. So therefore, if we differentiate this whole thing, if we differentiate this side, it's going to be the 2x plus 2y dy over dx. And if we differentiate this side, if we differentiate the xy, it's the x dy over dx plus y, and then the 6 just goes away. So we've differentiated the whole thing here by differentiating both sides. And now what we're going to do is the terms that have dy over dx, we're going to group them together on the same side of the equation. So what we're going to do is we're going to move this 2y dy over dx onto this side, such as we get this now, and then this y, which doesn't have dy over dx, we're going to move this onto the other side of the equation, such that we get this here. The good thing about this is because on this side of the equation both the terms have dy over dx, what we can do is factorize out dy over dx, such as we get this here, and then we can divide both sides by x minus 2y, so we can move this onto this side as the denominator and get dy over dx is equal to 2x minus y over x minus 2y, and this is dy over dx in terms of y and x. Now just quickly, you may not always need to rearrange it into dy over dx and make dy over dx the subject. The question says, though, in this case it says find dy over dx, but we'll go through questions in this video where that's not actually necessary. So here's another example where we have an equation like this and we need to find dy over dx in terms of y and x. So we need to differentiate both sides. So let's start with this side here. So we need to differentiate this, and we need to use the chain rule because we have the inner function, which is this 1 plus y, and the outer function, which is this power of 4 here. So the chain rule is the inner function differentiated, so this 1 plus y differentiated. If you differentiate 1, remember it's a constant, so it just goes away, and if you differentiate y, it's dy over dx. So this is the inner function differentiated, it's just dy over dx. And then the outer function differentiated is this power of 4 differentiated, so it's this comes down as a coefficient, so it's going to be 4. This 1 plus y stays the same, and now it's going to be to the power of 3 instead here. So this is 1 plus y to the power of 4 differentiated, and then if we differentiate this side here, x to the power of 3 differentiated is 3x squared, then sin y differentiated, so we're going to use the chain rule again with the inner function being y, the outer function being sin. So the inner function differentiated is just y differentiated, so it's dy over dx, and then the outer function differentiated is sin differentiated, so it's going to be cos y. So it's going to be dy over dx of cos y. So if we differentiate this whole thing, if we differentiate both sides, this side will now become the 4 dy over dx of 1 plus y to the power of 3, and this side will now be the 3x squared plus dy over dx of cos y. So what we're going to do, we need to get the dy over dx's all on the same side, so we move this here onto the other side, and then we factorize out dy over dx, and then we divide both sides by this and make this the denominator on this side. So dy over dx is this here. So now let's go through some past exam questions. So for this one here, we have a curve with this equation, and we need to find the points on the curve where dy over dx is equal to 0. So what we need to do, we need to differentiate this equation here, and we need to do it implicitly. So therefore we're going to differentiate this side and this side. So if we start with this side, if you differentiate x squared, you get 2x. If you differentiate 2xy, I've already gone through in this video how to differentiate xy using the product rule. If you differentiate 2xy, you get 2x dy over dx plus 2y. And if you differentiate minus 3y squared, again, I've already gone through in this video how to differentiate y squared using the chain rule. You get dy over dx multiplied by 2y. It's really, really common in implicit differentiation questions for them to include xy and y squared. They come up all the time. And then if you multiply this 2 by the minus 3 coefficient, you get minus 6y of dy over dx. If you differentiate 16 as it's a constant, it will just be 0. And on this side, if you differentiate 0, it will still just be 0. So therefore, if you differentiate this equation here, this side will be these terms added together. So 2x plus 2x dy over dx plus 2y minus 6y dy over dx. And on this side, it's just going to be the 0 differentiated, which is 0. Now, I talked about this before. With a lot of questions, you don't actually have to rearrange in order to find dy over dx and make it the subject like we did before, like this question here, because all we need to do is find the points on the curve where dy over dx is equal to 0. So what we can just do is set dy over dx to 0 for all of the terms where dy over dx is present. So this term here, as dy over dx is 0, is going to go away, and this term here is going to go away, such that we're just left with 2x plus 2y is equal to 0. So this is the equation we can use here. If we move the 2y onto the other side, we get 2x is equal to minus 2y. Divide both sides by 2 to get that x is equal to minus y. Now, this by itself doesn't tell us what the coordinates of the points on the curve are. But what we can do with this is sub this back into the equation here in order to find x and y. So we've got x is equal to minus y, so just sub in all of the values of x for minus y, or you could do it the other way around, y for minus x. I'll do it for x and minus y. So this is now going to become minus y squared plus 2 minus y for the x, y minus 3y squared plus 16 is equal to 0. So minus y squared is going to become y squared, and this here will now become minus 2y squared, and then it's minus 3y squared plus 16. All of these will become, so y squared minus 2y squared minus 3y squared is minus 4y squared, and then plus 16 is equal to 0. Move the minus 4y squared onto the other side, such that it's 4y squared is equal to 16. Divide both sides by 4, so it's y squared is equal to 4, and square root both sides, such that it's y is equal to plus or minus 2. Remember, when you square root, this plus or minus here. So we figured out that y is equal to plus or minus 2, so now we just need to find the respective x coordinates, and this is easy because we found out that x is equal to minus y. We found this equation here. So if y is equal to the positive solution, the y is equal to 2, then x is going to be equal to minus 2, so then one of the coordinates is minus 2, 2, and then if y is equal to minus 2, x is going to be equal to 2, so the other coordinate is 2 minus 2. So these are the two coordinates of the points on the curve where dy over dx is equal to 0. So let's do another exam question. So we're told that a curve has this equation here, and we need to find dy over dx in terms of x and y. So we're going to have to differentiate, and there's no way to rearrange this in terms of y. So what we're going to have to do is going to have to differentiate implicitly. So we have to differentiate both sides. So let's start with this side here, which is one term, the ye to the power of minus 2x. So we're going to have to use the product rule because we've got two functions multiplied together. So if we say that u is equal to y, then du over dx is going to be, and you differentiate y in terms of x, it's going to be dy over dx. And then if we say that v is equal to e to the power of minus 2x, dv over dx, this minus 2 is going to come down as a coefficient. So dv over dx is minus 2e to the power of minus 2x. So this differentiated is going to be, remember the product rule, it's going to be u multiplied by dv over dx, so it's going to be minus 2ye to the power of minus 2x plus v multiplied by du over dx, so it's going to be dy over dx e to the power of minus 2x. So that's this differentiated. And then if we differentiate the other side, if we differentiate 2x, it's just going to be 2. And if you differentiate y squared, we've gone through this loads of times in this video, again it comes up all the time, it's 2y dy over dx. So therefore, if we differentiate this equation here, this side is just going to be these terms here, and then this side is going to be the 2 plus 2y dy over dx. So we have this equation here, and in this particular question it wants us to find dy over dx. So this is a question like before where we actually have to rearrange in order to make dy over dx the subject and actually find dy over dx. So what we have to do is we have to put all the dy over dx terms onto the same side. So if we move this 2y dy over dx onto the other side of the equation, and we move this minus 2y e to the power of minus 2x, as it doesn't have a dy over dx in it. If we move this onto the other side, now we've got all of the dy over dx terms on this side. So now we can factorize out dy over dx to leave us with this here. And if we divide everything by e to the power of minus 2x minus 2y, we get that dy over dx is equal to this here. So for part B, we're told about a point P that has the coordinates 0, 1, and we need to find the equation of the normal at this point P. Now recall back to year 1 of chapter 5 where we talked about the equation of a straight line. The formula for the equation of a straight line is given here, and in order to use this formula we need two things. We need a coordinate on the line, so the y coordinate and the x coordinate, and we also need the gradient of the line. Okay, well we know a coordinate on the line because we're told that it's a normal at the point P, so therefore it's going to pass through the point P, and we know that the point P is 0, 1. So we know a coordinate on the line, so we just need the gradient of the line. Now go back to the year 1 differentiation video titled Tangents, Normals and Increasing and Decreasing Functions if you need a reminder of what the normal is. I'll go through it quickly here and how to find the gradient of the normal. So if we have a curve and we have a tangent, so a tangent touches the curve at a particular point, and in this question it's the coordinate P. And the property of a tangent is that if the gradient at this point on the curve is m, for example, then the gradient of the tangent is also going to be m. The gradients are going to be the same. And the normal is perpendicular to the tangent. It's 90 degrees from it. So this is the normal. And remember what the gradient of a perpendicular line is. It's going to be the negative reciprocal of the gradient. So the gradient of the normal is going to be the negative reciprocal of the gradient of the tangent. So in this case, as the gradient of the tangent is m, it's going to be minus 1 over m. And we can figure out the gradient of the normal. We can figure out this minus 1 over m because we can figure out the value of m, which is the gradient of P on this curve. And the reason that we can do this is in part A, we figured out an equation for dy over dx, and we know what the coordinates of P are. It's x is equal to 0 and y is equal to 1. So if we sub in x is equal to 0 and y is equal to 1 into dy over dx, which is what I've done down here, and if you put this into your calculator, you get out a value of minus 4. So dy over dx is equal to minus 4. So this is the gradient at P. So this is this m value here. So it's minus 4. So therefore the gradient of the tangent is also going to be minus 4, as that's the gradient of P, and therefore the gradient of the normal is going to be minus 1 over m, so minus 1 over minus 4, which is going to be 1 over 4. So therefore the gradient of this line, the gradient of the normal, is going to be 1 over 4, and therefore we can use this formula here for the equation of a straight line. So it's going to be y minus y1, so this is the y coordinate of P, which is going to be 1, is equal to m, which is a quarter, which we've already discussed, is equal to x minus x1, which is the x coordinate of P, which is going to be 0 here, and we can simplify this to y minus 1 is equal to a quarter x. Now it specifically wants it in the form ax plus by plus c is equal to 0, where a, b and c are integers. So what we're going to do, we're going to move this y minus 1 onto the other side to get that quarter x minus y plus 1 is equal to 0, and as it wants a, b and c as integers, we're going to multiply everything here by 4 to get rid of this fraction here, such that it becomes x minus 4y plus 4 is equal to 0, and this is the equation of the normal. So here's another past exam question where we're told that a curve has this equation here where P and Q, so P and Q here are just constants, so they're just numbers, and we need to show that dy over dx can be written in this form here. Now when you first look at this question, especially this part here with all the letters, it looks really difficult, but this question is just the stuff that we've covered already in this video. The only difference is that they've added these P's and these Q's here to make it more complicated, but these are just numbers, these are just act as coefficients, so we can kind of just ignore them for the most part. So we need to differentiate this implicitly because this equation has got a mix of x's and y's here. So we need to implicitly differentiate, so we need to differentiate both sides. So let's start with this side here. So if we differentiate px to the power of 3, the 3 coefficient is going to come down, so it's going to become 3px to the power of 2. Now like this here. If you differentiate qxy, we've already gone through in this video how to differentiate xy, with the q in front of it, the coefficient, we're just going to say that u is equal to qx, so du over dx is now just going to be q, and then if v is equal to y, then dv over dx is going to be dy over dx. So therefore if you use the product rule, it's going to be qx dy over dx plus qy, like we've already talked about in this video. And then if you differentiate 3y squared, again we've already gone through y squared in this video, it's dy over dx multiplied by 2y, and with this 3 at the front multiplying the 2, it's going to become 6y dy over dx. And then this 26 here, remember when you differentiate a constant, it's just 0. So therefore, if you differentiate this equation here, if you differentiate both sides, this side here is going to be these terms added together. So the 3px squared plus qx dy over dx plus qy plus 6y dy over dx. And then the other side, this 26, when you differentiate, is just going to be the 0 here. Now in this question, we need to find dy over dx, and we need to put all the dy over dx terms onto the same side. So if we move this 3px squared and this qy onto the other side, like we've done here, so we've got the dy over dx terms all together on this side here, and then we can factorize out dy over dx here to leave us with qx plus 6y, and if we divide both sides by this qx plus 6y, we get dy over dx is equal to minus 3px squared minus qy over qx plus 6y, and this is in this form here when we need it to be, where a is equal to minus 3, b is equal to minus 1, and c is equal to 6. So for part B, we're told about this point P, which is minus 1, minus 4, which lies on the curve, and we're told the normal at this point has this equation here, and we need to find the values of P and Q. Now there's a few ways that you can do this question. When I first read this question, the first way that I tried was to, because we know what the point P is, I sub this into dy over dx in order to find the gradient at P in terms of P and Q. And as it's the normal, we talked about before, the relationship between the normal is it's the negative reciprocal of the gradient. So that means that we would have the gradient of the normal and a point on the normal, which is minus 1, minus 4. So then we can use the formula for the equation of a straight line here and then get it into this form here and then compare coefficients. That's the first way that I thought to do it, but as I was going through it, I realized it's quite like complicated numbers. The algebra gets quite full on. And I looked at the mark scheme, and the way that they do it is a lot simpler in my opinion. It's a lot nicer, so that's the way I'm going to go through. But as I said, there's a few ways that you can do this question. So when it says that we need to find the value of p and q, we need to find two values. So that's telling us that we're going to need a pair of simultaneous equations. So we need two simultaneous equations. How do we get those? Well, the way that we can get one pair of simultaneous equations is we're told the point P lies on C. We don't actually need this part here to start off with. We're told that this point lies on the curve, so we can just sub this x and y value into this equation up here and get a simultaneous equation in terms of P and Q. So that's what I've done here. I've subbed in x as -1 and y as -4, like this here. And then if we simplify this, so -1 to the power of 3 is still -1, so it's going to be minus p. And then -4 times -1 is going to be 4, so it's going to be 4q. And then -4 squared is going to be 16, and then 16 times 3 is 48. So we get this here, and then if we move this 48 onto the other side, we get minus p plus 4q is equal to -22. So this is one simultaneous equation. So how do we get the second simultaneous equation? Well, this is when we use this second bullet point here, where we're told that the normal at P has this equation here. And what we can do with this equation here is we can rearrange this into the form y is equal to mx plus c, where m is the gradient, so we can find the gradient of the normal. So if we do this, so let's move this 19x and this 123 onto the other side, such as we get this here, and then divide both sides by 26, such as we get the equation of the straight line in the form y is equal to mx plus c, like this here, where m is equal to minus 19 over 26. So the gradient of the normal is equal to minus 19 over 26. And we've already talked about the relationship of the gradients between the point and the normal. It's the negative reciprocal. And if you don't know, the negative reciprocal works both ways. So if we're trying to go from the gradient of the point P to the gradient of the normal, here, as we already know, we get the negative reciprocal. It works the other way. If we're trying to go the way back, we take the negative reciprocal of this value here. So in order to get the gradient of the point P, we take the negative reciprocal of the gradient of the normal. So we take the negative reciprocal of this here, so we get rid of this negative sign here and flip around this fraction. So that means that dy over dx at this point P is going to be 26 over 19. And what we can do with this is we can create a simultaneous equation using dy over dx here, with dy over dx being this 26 over 19 that we've just figured out, and it's at the point P, which is -1, -4. So sub this in as x and y. So that's what I've done here. So we have another simultaneous equation, as I said, by subbing into the dy over dx equation. X is equal to -1, y is equal to -4, and dy over dx is equal to 26 over 19. So we can simplify this. So -1 squared is just 1, so this is still going to be minus 3p. And then minus q times -4 is going to be 4q. Q minus 1 is going to be minus q, and 6 times -4 is going to be minus 24, and this is still equal to the 26 over 19. So what we can do is we can multiply both sides by this minus q minus 24 to get rid of this denominator on this side and get rid of the fraction, which is what I've done here. And then we can expand this, so this multiplied by this is going to be minus 26 over 19q, and this multiplied by this is going to be minus 624 over 19. And then we can move this onto this side to pair these together, so it's going to be 4q plus 26 over 19q is going to be 102 over 19q. So we have this simultaneous equation here, which is in the same format as this one here now. Now, we've talked about before, we can either do substitution or elimination to deal with simultaneous equations. I'm just going to do elimination, so I'm going to multiply this simultaneous equation here by 3, because we have minus p here and minus 3p here. So if we multiply this whole thing by minus 3, this now becomes minus 3p plus 12q is equal to minus 66. So then these two coefficients are now the same. So if we minus this whole simultaneous equation here from this one, these two are going to cancel out. and then this 12q minus 102 over 19q is going to be 126 over 19q, and then minus 66 minus 624 over 19 is going to be minus 630 over 19, and then divide both sides by 126 over 19. So q is equal to minus 5, and then we can simply just find what p is by subbing this q value back into this simultaneous equation over here. So 4 multiplied by minus 5 is going to be minus 20, and then move this minus 20 on the other side, so it's going to be minus p is equal to minus 2, so then p is equal to 2. So therefore, after all of that work, we have found that p is equal to 2 and q is equal to minus 5. So here are two final past paper questions on implicit differentiation. For this second one, I tried to make it as big as I could on the screen. This is kind of the best way I could do it. It starts here and then this part continues up here like this. It's just the biggest way that I could get it. If it's still not big enough for you to see when I go through each particular section, I'll enlarge it. But have a go at these questions, pause the video, and I'll go through the answers in about 5 seconds. So for question 1, we're told about a curve with this equation here, and we need to find the exact value of dy over dx at these coordinates here. So we need to differentiate, so we need to find dy over dx, and we can't make y the subject of this equation, so we're going to have to differentiate implicitly. So we have to differentiate both sides of this equation. So if we start with this side here, and we start with the 2 to the power of x, this doesn't come up often, but you do need to be aware of it. We talked about it in the first video in this chapter titled Differentiating Sin, Cos, Exponentials and Logarithms. If you have y is equal to a to the power of x, then dy over dx is equal to a to the power of x multiplied by the natural log of a. So we have 2 to the power of x. If we differentiate it, it's going to be 2 to the power of x multiplied by the natural log of 2. This doesn't come up often, but you do need to be aware of it. And then if you differentiate y squared, we've already talked about in this video how to do this using the chain rule. We get 2y dy over dx. And then if we differentiate this side here, again, we've talked about in this video how to differentiate xy using the product rule. If you differentiate this, you get 2x dy over dx plus 2y. Again, it's very common for them to ask about y squared and xy like this here. So therefore, if we differentiate this thing, this side is going to be these terms added together, so the 2x natural log of 2 plus 2y dy over dx, and then this side is going to be this term here when you differentiate this, so it's going to be 2x dy over dx plus 2y. And we need to find the exact value of dy over dx at these coordinates here. So x is equal to 3 and y is equal to 2. So we can sub these values in already for x and y. So that's what I've done here for x is equal to 3 and y is equal to 2. And now we can simplify this from here. So this is going to be 2 to the power of 3, which is 8. So it's going to be 8 natural log of 2, and then 2 times 2 is 4. So it's going to be 4 dy over dx. 2 times 3 is 6. So it's going to be 6 dy over dx here, and then 2 times 2 is 4. So we've got this here. So we need to find the exact value of dy over dx. So we're going to have to make dy over dx the subject. So what we can do, we can move this 4 dy over dx onto this side. So we're going to be doing 6 dy over dx minus 4 dy over dx. It's going to be 2 dy over dx here. And we need to make this the subject. So let's move the 4 onto the other side like we've done here. And then we can divide both sides by 2 to get rid of this 2 here. So we get dy over dx is equal to 4 the natural log of 2 minus 2, and this is the exact value. It wants the exact value, so we need to write it in the log form of dy over dx at these coordinates here. So for question 2, we're shown figure 4, which is this here, and this graph has this equation. And actually this graph isn't relevant for part A, it's relevant for the latter part, so kind of ignore these north and east parts here, they're not relevant at the moment. All we need to do for part A is show that dy over dx can be written in this form here, so we just need to focus on this equation here, and this is the stuff that we've done before. So we need to differentiate this implicitly, so we're going to do both sides. So if we start with this side, if we differentiate x squared, it's just going to be 2x. If you differentiate minus 2xy, again we use the product rule and we get minus 2x dy over dx minus 2y. And then if you differentiate 3y squared, we use the chain rule in order to get dy over dx times 2y for the y squared part, and we've got this 3 coefficient that will multiply the 2, so 3y squared differentiated will be 6y dy over dx, and then this 50 here on this side, when you differentiate a constant, it's just 0. So therefore, if we differentiate this whole thing here, this side will be these terms added together here, so it's going to be the 2x minus 2x dy over dx minus 2y plus 6y dy over dx, and then this side will just be 0 here. So we've actually we can actually divide everything by 2 here, because these are all multiples of 2, and of course a 0 we can divide by 2 as well, so we can get it into this simpler form here. And now we need to show that dy over dx can be written in this form here, so we need to find dy over dx, and we need to make it the subject. So if we move the x minus y onto this side here, so all the dy over dx terms are on this side here, and then we factorize out dy over dx, so we've got this here, and divide both sides by 3y minus x, so dy over dx is equal to y minus x over 3y minus x, which is what's required. So for part B, this is kind of where this modelling aspect comes in, because we're told that the curve is used to model the shape of a cycling track, and the points P and Q, so P and Q here, are the furthest west and the furthest east points respectively, and we need to find the exact coordinates of the point P. So this is this one here, and this is the furthest west point. And the key to this question is realising that P and Q is kind of helped illustrated by this kind of straight lines here. P and Q, they sort of look like stationary points. They're not exactly stationary points, because stationary points go the other way round. So this is a stationary point here, and their gradients are a straight horizontal line, and the gradients are equal to 0. They kind of look like stationary points that have been rotated 90 degrees, where now these gradients are represented by straight vertical lines instead. So they sort of look like stationary points rotated by 90 degrees, and when we consider the gradients of these points, so the gradients of P, they're represented by a straight vertical line now. So the gradients are no longer going to be 0, the gradients are now going to be infinite instead. So therefore at P, dy over dx is going to be equal to infinity. Now this isn't technically really the way you say it, because you can't really be equal to infinity. The way we say it is that dy over dx is approaching infinity. But the reason this is useful to us, that at P dy over dx is approaching infinity, is when we look at dy over dx, the equation that we got in part A, this is going to be approaching infinity when we're dividing by 0. Remember, when we divide by 0, we can't do it. So we're approaching infinity when we're dividing by 0. And we're going to be dividing by 0 when the denominator is 0, so when 3y minus x is equal to 0. And this is an equation that we can use now, because what we can say, move this x onto the other side, so 3y is equal to x. And this here, we can sub into the initial equation for x and y here. 3y is equal to x. So we can sub in x is equal to 3y for all of the x values, which is what I've done here. And then we can work with this and then find what y is. So what we can do, we can say that 3y to the power of 2 is 9y squared, and then 2y multiplied by 3y is going to be 6y squared, like this here. Then all of these terms are y squared, so what we can do is we're going to do 9 minus 6 plus 3, which is 6. It's going to be 6y squared is equal to 50, and then divide both sides by 6, so y squared is equal to 25 over 3, and then square root both sides, so y is equal to, if you put it into your calculator, plus or minus 5 root 3 over 3. So these are the y values for Q and P here. So how do we know which one is P? Well, we can just do this by observing the graph here, because we can see that P is under the x-axis, so y is going to be negative. So therefore it's going to be the negative square root, that y is equal to minus 5 root 3 over 3. So we've got the y coordinate for P, and the way that we just figure out the x coordinate is just by subbing it into this equation here. So x is going to be equal to 3 multiplied by this y value here, and then these two are just going to cancel out, so x is equal to minus 5 root 3. So therefore the coordinates of P here, the exact coordinates, are going to be minus 5 root 3 for the x value and minus 5 root 3 over 3 for the y value. And then for part C, it says that we need to briefly explain how to find the coordinates of the point that is furthest north, and we don't need to carry out the calculation, we just need to explain how we do it if we needed to. And you can see that the furthest north point here, so this is the one with the biggest y value, is going to be this one here, and you can see that this is actually just a normal stationary point. You can see where its gradient is a horizontal line like this. So this is where dy over dx is equal to 0. So then if we look at our equation for dy over dx, it's this here is equal to 0. And then we can multiply both sides by this 3y minus x to get rid of this denominator. So y minus x is equal to 0. And then y is equal to x. So what we would do, we do the same thing as before. We would simultaneously solve the equation here with x and y, and the y is equal to x that we got before. Now, there's one other important clarification you need to say with this one, and it's similar to what we did before. Do you remember that we actually got two solutions, because when you square root you get a positive and a negative solution? We got the solution for p, but we also got the solution for q as well. This is going to be the same for this question, so we're looking for the furthest north point. We'll also get the coordinates for the furthest southern point here, because this is also an ordinary stationary point where dy over dx is equal to 0. So when we get in that same situation where we square root and we get a positive and a negative solution, we need to choose the positive solution, because the x and the y values for the northern point are the positive values. If hypothetically they were asking about the furthest southern point, then x and y are negative, so we would choose a negative solution.